Let's talk about eigenvalues and eigenvectors. Afterwards, we see the application of the eigenvalues and eigenvectors in terms of being able to force a matrix, a square matrix, to be diagonalizable, or to force it to be a diagonal matrix. And we can talk about similar matrices, and we actually define that. And that's also based on eigenvalues and eigenvectors. And then we're able to solve a system of differential equations, and you'll be thrilled to know that the differential equations, even from the DE course, those values that you were getting were actually based on the eigenvalues and eigenvectors that we'll deal with here in linear algebra. So we start with this idea of eigenvalue. It's the idea or the term that means characteristic, um, from a German word of eigen. Um, Here it's very just a special number, if you will, and so we have with matrices, square matrices, we have this idea of being able to extract some kind of eigenvalue, and then based on that eigenvalue, we can find a vector that's associated with it. If A is a square matrix, an n by n matrix, then a vector x in Rn is called an eigenvector of A if A times x is a scalar multiple of x. That is, the system AX is equal to this scalar multiple, lambda times x. Here, for some scalar, that is called lambda. Lambda is then called the eigenvalue for the system. Here, again, the word eigen, characteristic, somewhat is synonymous. The characteristic equation is based on the determinant. If A is an n by n matrix, then lambda is an eigenvalue of A if and only if it satisfies the equation, the determinant of lambda times I minus A is equal to 0. And sometimes we'll write this as, we have several ways of writing the determinant, but we can write the determinant with this notation. And due to my left-handedness, um, my lambdas are, being that we think right brain, the mirror image in my head, uh, the lambda comes out somewhat backwards. So, but anyway, um, this equation here, this determinant of lambda times I minus A is equal to 0 is called the characteristic equation. So we'll solve that, and once you solve that, you can get the eigenvalues. So here, this theorem is pretty neat, that if A is an n by n triangular matrix, then the eigenvalues of A are the entries along the main diagonal. Note here the eigenvectors form a basis, and we call this basis the eigenspace. Here, this theorem for eigenvalues of a triangular matrix. Looks like I'm repeating myself. Well, that's interesting. If A is an n by n triangular matrix, then its eigenvalues are the entries along the main diagonal. How did that happen? Boy, it did. Boy, I must be losing it, right? Um, well, no problem. So we're going to go ahead and begin, and the process is very easy. First, we find the eigenvalues, then from there we find the eigenvectors. So if you take this problem here, let's call this matrix A. And so we want to find the determinant of lambda times the identity matrix minus A. So first, let's just write it out. So we have lambda times the identity minus A. The identity matrix is matched up with the size of the matrix A. So we have lambda times 1 0 0 0 1 0 0 0 1, and then minus the matrix A. 0 negative 3 9 negative 4 4 negative 18 0 0 and 4. And so this becomes just the lambdas along the main diagonal minus 0 negative 3 9 negative 4 4 negative 18 0 0 4. And so what that gives us is lambda, well, minus 0, and that's just lambda, and then 0 minus a negative 3 is positive 3, 0 minus 9 is negative 9, 0 minus a negative 4 is positive 4, lambda minus 4 is that middle term, and then 0 minus a negative 18 is positive 18, then 0 minus 0 0, 0 minus 0 0, and then lambda minus 4. Alright, so this is the matrix, but we need the determinant. So I'm just going to write it as the determinant here. So this is lambda 3, negative 9, 4, lambda minus 4, 18, 0 0, and then lambda minus 4. So I'm going to do cofactor expansion along the, I have those two zeros, I'm going to use cofactor expansion along that last row. So that's lambda minus 4 times, you remember with that we delete its row and column, and so that gives us lambda times lambda minus 4, and then that's minus 12, and that's set to equal to 0. So that gives us lambda minus 4. Well, this is lambda squared minus 4 lambda minus 12. Let's see if we can factor that. That's lambda minus 4 times, looks like lambda minus 6 and lambda plus 2 equal to 0. So we call this equation, we put it in yellow, this is called the characteristic equation, and you can see it there. Now once you solve for x, this implies that we get the values for lambda, that lambda is equal to 4, lambda is equal to 6, and lambda is equal to negative 2. These values are the eigenvalues. So now we find the eigenvectors based on that. So let's see what happens here. So take lambda equal to 4, and notice how my order would be out of order from how he has it. He's starting off with negative 2, 4, and 6. It looks like he likes to list his, always says enter your answers from smallest to largest. Well, that's good to know. I didn't see that, so that's good. So now we know his order. Most of the way I do it, I just write the eigenvalues. It's not necessary to write them from least to greatest, but you know Web Assign is going to grade it like that. So by all means, put that information in there based on the way they want it. So it's the negative 2, 4, and the 6. Um, so if lambda is equal to 4, we're actually looking at this matrix here. I'm going to plug in lambda equal to 4 and then reduce that matrix on our calculator, reduce row echelon form, and then solve the system. And we do that 3 times because we have 3 eigen values. So if lambda is equal to 4, we plug that into that matrix, and that gives us 4, 3, -9, 4, 0, 18. Just replace lambda with 4, 0, 0, and 0. Okay. Now on the graphing calculator, when you reduce that, this is what I get. And so notice that that last row, I get all zeros. So that means that I'm going to have infinitely many solutions. We get that for all of them. Basically, what you've done in the process of the so-called eigenvalue to get that characteristic equation, that is, when you solve this, you are forcing A to have infinitely many solutions. You kind of think about it, it seems like we're breaking A to get something very neat from it, to extract some very neat properties that will take us a little bit further than where just A itself would take us. So there's something inside of A, but to get to it, we kind of have to crack it open. And so we do that uh, by using this pretty sophisticated equation. Pretty good, huh? The color I'm using is supposed to be black. So all we're doing here is just basically finding the infinite many solution set. The same thing back in chapter 1. So it's like you're not learning anything new. So we just apply that. So notice that on the main diagonal, it's that this term, come on, this term here, that term there, and that term for that one. Oh, not that term there. It'd be this term and that term. Because you have to rewrite these second two matrices. We'll get to that when we get to it. Let's just deal with this first one here now. So you let x sub 3 equal to t. Now the first equation is x sub 1 plus 9 over 2 x sub 3, but that's t, is equal to 0. So we get x sub 1 is equal to -9 over 2t. Now that second equation is x sub 2. Is that a -9? I got it so small. -9t is equal to 0. So here that gives us x sub 2 is equal to 9t. So the vector that we want, let's call it the eigenvector. It's little p sub 1. So we get x sub 1, which is -9 over 2. X sub 2 is 9, and then x sub x sub 3 is t. So it's just 1, and then, it's just times t. But the values that we use are these guys here for the so-called eigenvector. So we pick p sub 1, and if you say t is equal to 2, then we can kind of smooth it out, basically get rid of the fraction. So here p is equal to -9, 18, and 2. Okay. And that's where, I put mine out of order. I would have had the lambda equal -2 first, because it's the smallest, and then lambda equal to 4 is this number here, the -9, the 18, and the 2. Now, what if, let's say, or what if you pick -9 over 2, 9, and 1? That works too. And we're assigned to take that. You know, it better, right? Yeah, they're all equivalent. So that's cool. Now, you let lambda equal to 6, and you plug that into this matrix that we have here in yellow. Always go back to that when we're doing the row reduction. And blue is better. So when we do that, the matrix that we end up with is 6, 4, 0, 3, 2, 0, -9, 18, and 2. And then that's reduced to this guy. So you look at that. Now, can you look at that and tell what the eigenvector is? Do you see that that's going to be, okay, let's do it. Now notice that this matrix, that this one here is actually should be in that third row if you look at the terms. So basically this is x sub 1 plus 1/2 x sub 2 is equal to 0, and then that second row says x sub 3 is equal to 0. So x sub 3 goes out, it's 0. So x sub 1 depends on x sub 2, right? So that's what I was saying. If we reorder this matrix to see that, this ends up, just to be able to see that, this ends up looking like you have the 1, the 1/2, the 0, then the 0, 0, 0, 0, 0, 1. Then you look on the main diagonal. I just want to make sure that we put the 1 on the main diagonal. So at the x sub 2 is where we have the coefficient goes out. So we have a floating parameter. So we set x sub 2 equal to t. And then that implies that x sub 1 is equal to -1/2 t. And with that, this implies that p sub 2 is equal to, just going to write it here in this way because of the spacing. Come over here. P sub 2 is equal to x sub 1, which is -1/2 x sub 2. X sub 2 is 1, and it's going to be times t, and then x sub 3 is 0. Again, here you can get rid of the fraction by multiplying, by letting t equal to 2, or if you want, you can let it equal to, they let it equal to -2. I'm just going to leave mine as 2, and that's fine. And so in doing that, p sub 2 is -1, 2, and 0. So that's the one that I picked. -1, 2, and 0. It's equivalent as well to that. So it's not going to mark it wrong. And then when you have lambda equal to -2, you plug that back into that matrix, you end up with -2, 3, negative 9, 4, negative 6, 18, 0, 0, negative 6, and then that's reduced to this, and so that looks like x sub 1 minus 3 half x sub 2 equal to 0, and then that second row says x sub 3 is equal to 0. So kind of similar to what we had for lambda equal to 6. So x sub 3 is 0. We set x sub 2 equal to t, and then that implies that x sub 1 is equal to positive 3 half t. So this implies then that p sub 3 is equal to, and I got to write it in this way because I got this graph, this image from the calculator there. So x sub 1 is 3 over 2, and it's times t. X sub 2 is 1 times t, and then x sub 3 is 0, and that's times a t. And so if you just here for this case, just multiply by 2 to clear the fraction, we get p sub 3 is equal to 3, 2, and 0. And so you see that there. And then we get this here for that guy. Now these vectors form a basis for the vector space. Here, since we're dealing with eigenvalues, they form a basis for the eigenspace. Now, in the next sections that we deal with, you are asked to find a matrix P to be able to, one, force the matrix A to be diagonalizable. I have to get my syllables together. And then in the section for differential equations, that solution is based on the lambdas become your exponents for your exponential values. E to whatever power times t becomes e to the eigenvalue, but that's going to be multiplied times the same matrix P, and P is no more than just the so-called eigenvectors. So let me write that out for you here, and then I'm going to leave you alone. So for this particular problem, can't write with a highlighter. P the matrix P that consists of the eigenvectors written as column vectors will be used to force A to be diagonalizable. I guess I spelled that right. And this same matrix P is used in the solutions for systems of differential equations. So for this particular problem that we just got through doing, so the matrix P becomes, I had initially negative 9 over 2, and this was 9 and 1, and then we got negative 1 half, 1 and 0, and then we had 3 halves, 1 and 0. Now you could do the equivalence, how we converted that, and we ended up with negative 9, 18, just multiply that vector times 2. And then that next one, negative 1, 2, and 0, and then 3, 2, and 0. So either one is fine. They're equivalent. So that's going to be interesting, because to get the diagonal matrix, we'll say that let B be the diagonal matrix. It's equal to this P inverse, this matrix P, get its inverse, times the matrix A that we started out with, times P. And you can put this form directly in your calculator and just let the calculator reduce it, and you end up with the matrix that comes out of your calculator consists of a diagonal matrix with just the eigenvalues. So for mine, it was 4 first, 0 0, and then 0 6 and 0 0 0 and negative 2. Okay, so that's pretty cool stuff. Now this last page here is just extra. I'm going to cover it in the next section, but I'm through, and hopefully that helps. So if you have questions, just let me know.